Today our topic is on basically a blast furnace stoves, which is we can say the next evolution in iron making. And here is the thing: we have been building the stoves for over a century, but we have finally reached the next evolution of the heart of the furnace. On the screen, you see a glowing wireframe blueprint of the Kalugin Shaftless Stove. It's vibrant orange and yellow, showing three big targets. And all these three targets are very important. One is 1400 degrees centigrade hot blast, a 30-year lifespan, and the most critical is the shaftless design. Think of this like moving from a bulky desktop computer to a slick, high-powered laptop. So what it gives? It means you get more heat in a smaller footprint with way less maintenance. To understand why this is a big deal and it's an immense deal, we have to look at what currently breaking in our plant. So coming to the physical limits of conventional stoves. Have you ever noticed how our current stove seems to lean or crack over time? So look at these two diagrams. On the left is the classic copper stoves and those red circle shows the silent killers, the gas short circuit and the notorious banana effect. That's where the combustion chamber literally bends because it's too hot compared to the brick around it. On the right, the external combustion design solves the bending but adds a crossover vulnerability and inflate your costs by 30%. So what is the result? What is the resultant then? You are paying more money for a design that is still has a weak spot. We needed to simplify. So, eliminating the combustion chamber. So, here is the radical shift. What if we just got rid of the combustion chamber entirely? Uh, Describe this. You see uh, uh, see a nature of a stove with a massive glowing yellow cross over the traditional internal tube. By stripping away that tube, 100% of the internal cylindrical space is now dedicated to heat storing checker works. So we are not just guessing if this work. There are 179 units already running clubly. So you maximize your heat storage without the structural banana risk. But you might be wondering, how do we burn gas without a chamber? Now this slide talks all about the curiosity that generated just now. So slide 4, as it shows the jet vortex combustion. How do we keep a fire stable without a pipe to hold it? Look at these three steps on the screen. First you see blue and orange arrow merging in an annular supply. Then look at that beautiful swirly colorful circle in the middle. That's the vortex mixing. It's like a tornado of fire stabilized in the dome. Finally, the heat map shows the stabilization zone. And all these, that is, this jet vortex mixing ensure the gas is 100% burned before it even touches the brick. which completely stops that annoying acoustic flame pulsation. So it is all about the perfect thermodynamic distribution. So if the fire is stable, the heat should be even, right? So check out this graph. You see wavy red and blue lines for old stoves, but look at that flat white line labeled 3 for the Kalugin stoves. So it stays perfectly level across the entire radius of the checker chamber. So it's the difference between a shower head that only hits one shoulder and one that covers you perfectly. And what's the then result? So even heat means no localized thermal shock. So your brick do not crack and fail prematurely. Hexahedral checker works. Now let's talk about the batteries inside the brick. On the screen are two glowing hexagonal honeycombs. The high capacity variant has 19 holes, but the ultra dense one on the right has 37 holes, giving you 64 square meter of heating surface per cubic meter, which gives the massive result. This massive surface area lets you extract heat much faster. It's like having a radiator with more fins. It just works more efficiently. So 40 to 50% height reduction, and here is the thing that management loves. Height, look at this comparison. You see a tall dark blue stove next to a much shorter white. So we are talking about a 40% to 50% height reduction. So what it means? You get the exact same thermal capacity in half the vertical space. So it's a spectacle is that makes the whole structure more stable and easier to build. So what is the diagnostic matrix? So let's look at the scoreboard. This table compares all three architectures. Look at the right hand column for the cases. It hits excellent for the space efficiency, low for the construction cost, and zero for the creep risk. Compare that to Cowper's high creep risk. So what is the final? The cases is the only design that solves the physics and the budget at the same time. So let's dig into that budget. So stripping 38% of refractory weight, how much do you think 600 ton of high grade silica cost? Look at these bars. The external stove needs over 1613 ton of refractory while the cases needs only 992. That's a 38% reduction in weight. So what is the gain? So that's a massive gain, immediate saving on capex. You are buying fewer brick to get better performance. It's a literal weight off your shoulders and the foundation too. Shattering the emission standard. Now we cannot ignore the environment anymore. Look at this graph where the white line drops like a cliff. We are hitting less than 20 milligram per meter cube of CO. That is 5 times better than the strict, uh, uh, strictest European standard. This is not just a stove for 26, it's a stove for 2050. So you are future proofing your plant against environmental taxes also. So this slide, which is about a very important activity of pushing to 1400 degrees centigrade for 3 decades. So what is the grand prize? Three glowing gases, 1400 degrees centigrade hot blast, 30 years of zero repair life, and a 900 degrees centigrade base temperature to eliminate thermal fatigue. The silica dome architecture is what dictates that 30-year life. So you can focus on iron making instead of constantly planning your next stove reline. But can we actually fit this into an old plant? So this is a very bigger question. So seamless in situ integration. Yes, we can. So look at this photo of BF5. Those white wireframes you see over the existing facility show how compact KSS fits perfectly onto existing foundations. You don't need to clear new land or move mountain. So it's the perfect drop-in modernization for aging facilities that are stuck with failing external combustion stoves. Coming to the new baseline, and to wrap up this, look at these three pillars: engineering, economy, and environment. The cases doesn't just improve the process, it re-engineer it. By removing the combustion chamber, we unlock a cascading series of wins: less space, less cost, and cleaner air. And this is the new baseline for sustainable iron making. So let's stop building 19th century technology and start building the future.